All right, so now we're going to talk about enthalpies of reactions. And so we're starting notes here on the bottom of this one, but here we go. So enthalpies of reactions. So, all right, so like volume or energy, enthalpy can be calculated based on its change. It's delta H. Remember, enthalpy is a state function. We don't care how it gets from this point to this point, what reaction pathway it goes through to get to that point. We just know that all I care about is how I start here, how I finish here, and in this case, we're going to talk about the change in energy in between those. Okay, so that's what's going to lead to a bunch of the different ways that we can do this. Okay, so H, change in H equals H final minus H initial, but since we have two sides of a chemical reaction, we use that H, change in delta H is equal to the enthalpy, delta H of our products, minus the H of our reactants. Okay, and this is known as the enthalpy of the reaction or heat of reaction, and is written as delta H. So this is enthalpy or heat of reaction. Those two are used almost interchangeably. I probably will use them interchangeably, and I'm sorry because I tend to do that. So, but it's written as delta H of reaction. Okay. Now there's several ways to determine the heat of a reaction. And the first way that we're going to use is to be using a given set of values and performing stoichiometry with those numbers. Okay, so hydrogen balloons. You guys have seen me blow up hydrogen balloons before. So 2H2 gas plus O2 gas makes 2H2O gas. When I do that, the delta H for that reaction is negative 483.6 kilojoules. So let's talk about some observations that we see here that will probably be helpful as we work through this. So number one, the negative sign right here, this negative sign right in front of my big fat head, that negative sign means that this reaction is exothermic, which means that energy is being released. Okay. Now the amounts are not specified in the reaction. There's no point here that specifies how much stuff is unless we look here, here, and here. Okay. And so no amounts are not specified in the reaction other than the molar quantities listed. And so what does that mean? Well, that means that I can read this expression and say that for every 2 moles of hydrogen I combust plus every 1 mole of oxygen, I'm going to make 2 moles of water, and it's going to release negative 483.6 kilojoules of energy to do it. Okay? Now, when we write a chemical equation like this, we call it a thermochemical equation. All right? And so it's a chemical equation, but it also has thermal properties that we are taking into account. And that's important, okay? Because we are going to start taking into account those, and that's very important for pretty much everything we're going to do for the rest of the year. So we're going to look at that a lot, and so you're going to be kind of tired of looking at this stuff by the time we get there. Okay, now, when calculating our delta H using their thermochemical equations, there are some key things to take advantage of. So number one, enthalpy is an extensive property. Okay? I don't know if you remember the word extensive or not. And so what that means is that the quantity of how much is there matters. Okay, so an extensive property is a property where quantity matters. And so the quantity of the delta H depends on how much matter I am present or I have present. And so if I double the reactants and products in a reaction, I would double the heat released or gained. Okay, so if I double the reactants and products in equation, I would double the heat that is released or gained. Okay, and that's kind of a big deal too. So down here, here's CH4. So this is methane gas plus oxygen makes CO2 and water, and I'm releasing 890 kilojoules of energy when I do 1 mole of methane to do that. Now, if I double this reaction, where I would put 2, multiply everybody by 2, I'd have 2CH4, 4O2, 2CO2, and 4H2O, but my energy also goes up by 2 as well. And so this goes up to 1780 kilojoules, right there. 1780 kilojoules being released. And so there's still a negative sign there, but I'll write it in just in case. Okay, and so we doubled the energy. If I double the chemical equation, I double the energy. So that's kind of a big deal. Okay, if I didn't want to do that. I'm sorry. I do have to move this anyway, though, because I got to get to the bottom two examples. So we're going to erase this. So, this is 30 seconds of fun, right? Take a break, have a drink, you know, what you got to do. All right, here we go. Now, here we go. If I have B, which is where we are, is right here. I'm going to bring that all the way up because I don't want to do it. Okay. The enthalpy change for a reaction is equal in value, but in opposite sign if we reverse the reaction. So opposite sign if the reaction is reversed. Okay. So here's that same chemical reaction. CH4 plus O2, 2 O2 makes 1 CO2, makes 2 waters, 890 kilojoules of energy. If I flip the reaction, so my products become reactants and my reactants become products, my delta H value gets multiplied by -1. And so this goes from releasing 890 kilojoules of energy, as written, to being a positive 890 kilojoules of energy, which means to make this reaction happen, you'd have to put 890 kilojoules of energy into these products, or these reactants, to make these products. Okay, so if we flop the equation, we flop the sign of the magnitude. Okay, and the last one, the enthalpy of a chemical reaction depends on the state of matter of the product. So you need to be cautious of the phase and make sure that you look up the correct reaction. So water, taking liquid water and turning it into a gas requires 88 kilojoules of energy per 2 moles of water. And so we got to make sure that we look at that stuff too, because that matters. We have to make sure that we look at phase and take into account our different phases of matter so that we know what the phase is, so that we know that we're taking it correctly and doing it the right way. Okay? Now, the first reaction we're going to work through together is this one right here. And so when we're going to do that, we are going to look at, this is what is the enthalpy change for ethanol burning. Okay, so this is ethanol, 3 moles of oxygen to make 2 moles of CO2, 3 moles of water. We know that the delta H for this reaction as written is -55 kilojoules. Okay, now what is the enthalpy change for the combustion of 15 grams of ethanol? Oh man, so how do we do this? Well, we have, let me get the mouse out of the way, we have 1 mole of this stuff here. There's a 1. Let me erase the first one so it doesn't look like 11. So we have 1 mole of ethanol, 3 moles of oxygen, 2 moles of CO2, 3 moles of water. -555 kilojoules. Okay, so notice there's a 1 in front of it. It means that 1 mole of ethanol was burning to release that 555 kilojoules of energy. So we're going to start with our quantity of ethanol. We're going to convert it to moles, and then we're going to convert it to energy. So let me show you what I mean by that. All right, here we go. So we're going to do one sample problem right quick, and this will get you started, and we'll have a whole bunch more that we'll do in class. So let's do that. There we go. Then I don't have the words across my face. All right, here we go. Start with our 15.0 grams of ethanol. Okay, so 15.0 grams of ethanol. Okay, over 1. Now, we know that 1 mole of ethanol has a mass. We have to figure out what that mass is. Okay, ethanol is C2H5OH, so there's 2 carbon atoms, 12.0108 times 2. There are 6 hydrogen atoms, 1.00795 times 6, and 1 oxygen atom plus 15.9994. You're going to get something around 46.07 grams of ethanol. Okay, so now grams of ethanol are canceled out. So now I am in units of moles of ethanol. So I go back to my balanced chemical equation in the page above it here. I have, for every 1 mole of ethanol that I consume, I'm going to release 555 joules of energy. So every 1 mole of ethanol is going to release, that's why there's a negative sign there, 555 kilojoules. So moles are gone. Okay. So now 15 times 1 times negative 555 divided by 46.07 is going to give me a value of negative 180.7 kilojoules. Now, does this value make sense? So first off, we know that 1 mole of ethanol is 555 kilojoules of energy released. I have 15 grams, which is about a third, a little bit less than, but a third of the molar mass of ethanol, 46.07 grams. And so we would expect that our value would be a little bit less than a third of that 555. And so that's our proportional thinking. So that's what makes sense. We see this value, we see this number, but I want you making sure that you are able to look at that value and that number and make sure that it makes sense for what we did and where we're at. So that's one example of doing enthalpy of reaction. We're going to do a bunch more. You'll see a whole bunch more. So there we go.